So we want to be able to understand, predict, and ultimately control matter and energy at all length scales and time scales, and in particular those that are useful towards energy generation, production, storage, and so on, as well as this environment and society. So, as you know, one type of matter is a fluid, and so a fluid is able to transport energy and move around and as it flows. And but when a flow becomes turbulent, that one becomes disorganized and with a lot of organized structure and some random motions, the turbulent flows are able to transport and mix matter so that they can bring chemicals more closely together, so they can react chemically and mix diffusively. So what I'm going to talk about is that a particular application where we want to be able to predict the fundamental physics of complex turbulent flows so that we can use them and design engineering applications such as these. Okay, so these are typically, and so the complexity that I'm going to describe here has to do with how organized motion emerges from this random turbulent motion. And so we have various engineering flows and other astrophysical flows and so on. They have various body forces or other sources of ways that of a complexity that are more complex than a standard two-dimensional kind of turbulent shear flow on a wall or a boundary layer. Okay, and so this can lead to the generation of vortex rolls. And these are basically counter-rotating Streamwise vortices that are able to rapidly mix the low-speed fluid near the wall and the high-speed fluid near the wall so that the turbulence can sustain itself. But if you apply some perturbations or some other forces to these types of flows, you can cause these vortex rolls to break up. Okay, and so in the case that you may be familiar with on an airplane, very large airplanes often have swept wings, and so what this causes, it causes the flow that's coming nominally towards the plane to curve as it goes around, because there's a Spanwise pressure gradient that's pushing the flow outward away from the interior of the jet. Now, and similarly, there's also in, say, gas turbines, which are attached to these jet engines and to these airplanes. You may have forces of rotation and buoyancy that are important to be able to sustain these flows. Okay. And so, in the context of the Spanwise pressure gradients or effects of transverse strain, so just forces that are orthogonal to the mean flow direction, and what happens when you do that? So what happens is that the mean flow speed and the direction will change with wall distance. So I'm showing here a schematic of that flow that's going along an airfoil or wings on an airplane. And you can see that you have a mean velocity that's directed nominally in the direction of the free stream velocity. But there's also a development of a transverse or spanwise velocity component that varies with height. Okay, and so under these types of conditions, the turbulence is typically less efficient at extracting energy from the mean flow. Okay, and so this tends to reduce momentum and heat transfer rates. And so in terms of engineering application, people often will put vortex generators, things like this, to prevent the flow separation or stall that would occur under these conditions. And so you may have seen this if you looked out the window of an airplane and seen little protuberances that are situated on the sides of the wings here to be able to cause the flow to transition to turbulence and remain attached. Okay, and so similarly, you can also have these body forces and things like this that generate elongated Streamwise vortices, as shown here. And so, like I said, these Streamwise vortices, they ventilate the near wall turbulence and the large scale flow above it. And so this is important for what this effectively does is enhance the mixing and heat transfer in these types of flows. Now, so I'm showing just two examples. I mean, this type of flow configuration is very generic and occurs in many physical applications. But so in the context of, say, rotating shear flow, so if you had in a gas turbine these turbine blades, these are rotating. And so they're often rotating in such a way that on one of the sides of the airfoil, you'll be able to generate these longitudinal Streamwise vortices. Now, and since if say on a turbine blade, the incoming gas is very, very hot, and you want to be able to keep the turbine blades cool so they don't melt. And so if there are these vortex rolls that are there that are taking the hot fluid above the wall and bringing it near the wall, then that can cause the blades to become scoured or melt and have patches like that will occur. But you can also use film cooling, where you effectively generate streamwise vortices near the wall rather than in the large-scale flow, where you have cool flow that will is injected along the wall to be able to counteract that effect. And then you can also have this in other heated shear flow examples as well. Okay. So now this is a common type of flow known as Rayleigh-Benard convection. So this is what happens, for example, if you are cooking on the stove and you have a long, very large pot of water or something, let's say, and it's heated on the bottom. So you have a higher temperature on the bottom wall, and then there's an upper surface or wall that is cooler. And so you have these large-scale thermals that will rise and fall in this type of flow. And so this is just showing an example of how when you have just a vertical body force, in this case gravity, the acceleration of gravity, but with no mean shear flow, what the flow looks like. So you have these characteristic wavelength rolls, but these rolls are disorganized in this kind of spoken pattern, convection pattern. Now, if you were to now apply a mean flow to this in this direction, so that you now have a mean shear in this flow, those originally kind of disorganized roll patterns align themselves with the mean flow, and so this has consequences for being able to sustain the mixing and heat transfer in these flows. And so I'm going to talk about what happens when I take this flow and then distort it by applying a transverse force to it. Okay, and so, like I said, these three-dimensional boundary layers, when you have these transverse pressure gradients or surface curvature and so on, they tend to reduce mixing and heat transfer, but these vortex rolls tend to enhance mixing and heat transfer. And so we're just going to consider the case when they interact together, when you have a mean shear, but with at time t equals 0, an impulsively applied pressure gradient in the Spanwise direction to evaluate how do these two competing effects interact. And so this is another common example where you would see this if you were flying on your airplane, you looked out the window, you'd also see this. You would see clouds that would form, and they're often very often seen to be in these roll patterns of these elongated streamwise vortices of counter-rotating cells where you have these patterns. Now, it's not the fact that the clouds are there isn't all that important. This is actually a very common feature of the unstably stratified atmospheric turbulence. But this is what happens. So this is what you see here. So up over here is Russia. This is the Caspian Sea. Down here are the Caucasus Mountains on the western side. And so the flow in it is initially, the mean wind is initially going in this direction. But these mountain ranges that kind of imposes, this topography imposes a slight Spanwise pressure gradient into this flow, causing some breakup of these rolls further downstream, as you see here. And so this is a generic feature of wall-bounded turbulent shear flows that you can see at larger and smaller scales. Okay, so now if you look closer, right, so these rolls are nicely aligned and all of this, but we might want to consider what's the effect of, in terms of where do they sit, because this is the same type of consideration that you would have in, say, a gas turbine or heat exchangers and things of this sort. So, so this is just a grid that I just overlaid on top of this picture, and with spacing of about 25 kilometers between each grid point. And so you can see that these elongated counter-rotating vortex rolls that are persistent in this layer are much smaller than this particular grid size, but that if you wanted to capture them, you'd have to have a much finer Spanwise resolution to be able to resolve this and the heat transfer and the scalar transport that they bring about. So this is a classically well-known example that while you grid, say in a turbulent flows, you very often have smaller Spanwise spacing. Because of these organized structures are preferentially aligned in one direction rather than the other, and to resolve them, you need to consider this effect. Okay, so like in the example I showed before, so what we have because this is a very large aspect ratio domain, and so to be able to resolve these large-scale organized structures, we want to be able to see what's necessary. So this is a picture of the Spanwise spectra. So basically, if I were to go back here and just fly an airplane through this cloud layer, say here, and collects the velocity or temperature spectra along this line, the peaks of these organized structures would show up in the spectra. So that's what I'm doing in this picture. Okay. And so in effect, you have an inertial kind of range turbulence over here interacting with the discrete large-scale instabilities of the large-scale flow. And so we want to be able to clarify some of these interactions and to see how this affects, say, maybe the synoptic scale pressure gradients that occur that actually are what drives the mean energy into this flow, and how do they cascade down. So, all right, so now if we consider in that same configuration, what's the heat transfer in this flow. So this is a plot of the Nusselt number. So this is just a measure of the kind of the mean heat transfer in this flow. How fast is energy being transported from the bottom wall to the top, and so on. Okay, and so at time t equals 0, I take this initially 2D, just a flow with just a vertical body force and a mean shear, and then I apply a Spanwise pressure gradient, and the flow will churn in that new direction as the mean velocity equilibrates. And so there's going to be some interactions. And so what you see is that the heat transfer is initially somewhat high, but then it drops, but then it recovers after this non-equilibrium flow becomes the flow is basically just changing direction and aligning in a new flow direction. But in this part of the region of the flow, these large-scale organized structures are being broken up, and so this has consequences for the ventilation of the hot and cold fluid near the wall. Okay, and so of course, if you have a larger forcing, you can bring this heat transfer down further, and so this is shown here. So if you had say in an atmospheric case, so what this is showing, so this is each of these lines is separated by 10 units of time, and this corresponds roughly to about 200 seconds or a few minutes of time in, say, an atmospheric flow. So this light blue line is the initial state, and then as you apply, as the flow is churning, the temperature becomes almost linear, close to linear, much more so than what you would typically find in a regular turbulent shear flow, and then it begins to recover. Okay, and so this is an important aspect of this. So, okay, so now I'm going to show what happens just kind of in a visualization, and to see. So what I'm showing here now is a slice near the wall, so that we can see how the near wall streamwise streaks and the large-scale counter-rotating vortices, how do they interact? Okay, and so again, at time t equals 0, I'm going to apply this impulsively applied pressure gradient and see how the flow develops under this condition. And so white here is the hot fluid. So this is the rising thermal plumes. This is a temperature plot, and the darker colors are the cooler plumes that are hitting the wall beneath here. Okay, and then down here is a plot of the Nusselt number, like I showed before, and as a function of time. And so as I apply this pressure gradient at time t equals 0, okay, the flow begins to move in the Spanwise direction. So this is a viscously driven type of flow. You're just accelerating things now in the orthogonal direction to the mean flow. Okay, and so we go a little further. Now things are accelerating a little faster. Okay, and the one side of these rolls is, because in effect you have these counter-rotating rolls, and now the near wall fluid is becoming differentially accelerated with respect to the fluid above it, and so there's some mixing that's coming into play here. Okay, as these rolls now realign themselves. So go farther along in the time. So near the minimum. What you see here is that the smallest scales of the streamwise streaks near the wall respond most quickest to the new flow direction, because in a sense, what you'll see is that these rolls that are aligned in this direction will now become aligned in this direction at long time, and okay, and then the heat transfer is reduced. So in effect, what you're doing is you're breaking up these large-scale organized kind of motions that are keeping, that are mixing the flow, and when you break them up, there's nothing left to bring the low-speed fluid near the wall up and the high-speed fluid down near the wall. And so we're trying to see kind of how this counteracts each other. Okay, and so eventually, this is almost as if you had put a rug on the bottom of the wall, and so so you just have that very hot fluid here, and so that if this is, if there was a gas turbine or things like this, this would not be a situation you want to find yourself in, or where it would be if it was the hot fluid. So anyway, so then eventually the flow is now becoming aligned more and more so, and so we see now that the same large-scale instabilities then emerge once the flow becomes stabilized. Okay. So what I've shown is that these, when you have these, what I've described is when you have this transverse strain, this tends to reduce mixing and heat transfer in the flows, but if these large-scale organized vortex motions, they tend to enhance mixing and heat transfer, and when they interact, due to an impulsively applied transverse pressure gradient, these rolls will break up, temporarily reducing the vertical transport, but eventually they'll recover, and so we want to understand this. So thank you.